Physics students, this is Dr. Brenzi again, and this is lesson 10.1, video number 2. In the first video, which hopefully you just watched a moment ago, what we discovered is that temperature is a measure of the amount of kinetic energy each molecule has in an ideal gas. But then I left you hanging there because I said, well, not quite, because we made a couple of assumptions that don't really occur in actual gases. So let's review what those assumptions were and then deal with those assumptions so that we get a more accurate picture of what temperature really is and what it really measures. It does measure kinetic energy, but it's not exactly this relationship that I gave you here. So let's go and do that. So let's go on to our first assumption here. So the first assumption that we made is we assume that the gas molecules only move in one dimension. They either move in positive x or negative x. Well, what we really know is that gases move in 3 dimensions. If you remember the simulator from the last video, they were moving all over the place and they were colliding with not only walls in the x direction, but they were colliding with walls in the y and the z direction as well. So, how do we handle this fact that we actually have a gas in 3 dimensions? Well, let's think about the velocity vector of a gas molecule. And let's say that this image right over here represents the velocity of a gas molecule. And that gas molecule's velocity has an x component along here. It has a y component along here. And it has a z component along here. So the magnitude of this vector, its actual velocity, we can get by adding the 3 components, but not adding them as 1 plus 2 plus 3. We call it adding them in quadrature, which means we add them like we would do with the Pythagorean theorem. Let's see, for some reason. Oh, try that. There we go. So really the magnitude of that vector squared is equal to Vx squared plus Vy squared plus Vz squared. Well, how does that affect our result that we came up with? Well, we said that we know that the kinetic energy of a molecule is 1/2 times m times v squared. And v squared is this quantity right here. So what we should do is we should replace this v squared with this entire expression over here, like this. Now, each of these is a one-dimensional velocity. So what we could say is that m times vx squared is equal to k times t, just like we got in video number 1. But there's no reason that x is special. We could have called it the y direction. And if we call it the y direction, then we would get the same result for m times vy squared. And the z direction is not special, so we could have said that m times vz squared is equal to kt. So each of these components here, this component, that component, and that component, each of those is equal to k times t. So now, if we add all those together, what we really have for a 3-dimensional gas is that kinetic energy is actually 3/2 times kT. So that's how we deal with the first assumption that the gas only moves in 1D. In 3 dimensions, it becomes 3/2 kT instead of 1/2 kT. All right, now what about the second assumption? That second assumption we made is that we assume that all molecules in the gas have exactly the same speed. Well, actually, each of them has a random speed. They have a distribution of speeds. Some of them are going really slow, some are going really fast. And if you think about the little simulation that I showed you at the beginning of video 1, you can probably observe with your own eyes that all of those were going with different speeds. And each molecule wasn't even going at the same speed throughout the entire simulation. So these gas molecules have a random speed. So we have to deal with that. How are we going to deal with that? Well, let's take a basketball player. I just Googled basketball player on the internet, and this person came up. No, I'm kidding. I actually know it's LeBron James. So let's say LeBron, over 4 games, has these statistics. So in game 1, he scores 38 points, and then game 2, he scores 34 points. Game 3, he scores 32, and game 4, he scores 40 points. So if you add up his total throughout those 4 games, it's 144 points. Well, in order to figure out the total, do I need to know how many points he scored in each game? You might think yes, but actually the answer is no. Well, all I would need to know is, first of all, what is his average total? So if I average these 4 numbers, I come up with 36. And if I know how many games he played, what I can do is I can replace each of these point totals, ding, 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 and ding, with his average. So I put 36, 36, 36, 36, and I add all of those up, and I'm going to get the same total. So I only need to know 2 things about LeBron's performance over the 4 games. I only need to know his average points per game, and I need to know how many games he played. That's it. And then I can figure out the total number of points. Okay, well, how does this apply to a gas? Well, one of the things that we calculated in the gas is a total pressure. Now, let's apply the same principle that we did with LeBron's point totals to the pressure. So let's say that all we need to know is 2 things: the average amount of force per collision and the number of collisions. So again, pressure, the pressure on the wall, is equal to the magnitude of the total force divided by the area of the wall or section of wall. And we can say that that's equal, this total is equal to the average force acting on the wall per collision times the number of collisions. And divide that by area, because we have to take force divided by area. Well, what that means is that instead of getting n over v times vx squared, I can say that this is an average speed. And I'm going to get back to actually what this means in a second, because it's not quite average speed squared. I'll tell you what it is in a moment here. But for now, let's just say that this times this is going to give us, excuse me, sorry about that. Let's just say that this is the average amount of force times the total number of collisions divided by area. If you're not sure how I came up with this, you go back to video 1 when I talk about total pressure, and you'll see I come up with an expression like this, except instead of having these weird angle brackets, I just have Vx squared. Okay, well, what this tells me is that if I plug this back into the ideal gas law, like I did in the first video, I'm going to get m times this, what we call average for now, but it's not really an average, equals k times t. So, if I multiply both sides by 1/2, just like I did in the last video, and if I deal with this in 3 dimensions now, remember this is how we had to adjust our first assumption. Instead of Vx, I really have V squared, and instead of 1/2 kT, I have 3/2 kT. So now I can say the average kinetic energy of each particle is equal to 3/2 times kT. So that's the average amount of kinetic energy per gas molecule. Okay, so temperature is a measure of the average kinetic energy of a molecule in the gas. Now, let me talk about that funny looking V squared in brackets. Now, what this represents actually, it's called average of speed squared. Okay, sometimes you'll hear it mentioned as mean squared. And it's not equal to the square of the average speed. In other words, I'm not taking the average speed and then squaring that number. What I'm doing is I am taking the square of each individual particle's velocity, 1, 2, 3, 4, 5, and then I divide that number by n. So it's the average of speed squared, and that's what this represents. This is what we need to know to figure out the average kinetic energy of a gas. Of a gas particle, excuse me, a gas molecule. Now, to show you that those two numbers are not equivalent, so this is not the same as taking the average and squaring the average velocity, let's have just a quick data set. So we have 4 different velocities. So we have a gas that consists of 4 particles, 4 molecules. And let's say one of them has a speed of 5, then 6, then the third one has 3, and the fourth one has 8. Units, don't care about them. Let's square each of those numbers, and that's what I have in the right-hand column here. So I've just taken the square of this number to get this number right here. Now, if I take the average of these 4 numbers, 1, 2, 3, 4, I am going to get the average of speed squared. That's this number right here. Okay? So if I take those 4 numbers, divide it by the number of molecules in the gas, I get the average of speed squared is 33.5. Now, on the other hand, if I take the average of the 4 speeds, I get this number. But then if I try to square that, I don't get the same number. Okay, it's not going to be the same result. The thing that we do want when we're calculating average kinetic energy is this guy right here. The average squared. I'm sorry, the average of the speed squared. See, even I'm getting them mixed up. Okay. Now, if we take the square root of this average right here, this guy right here, if we take the square root of this, we have a special name for that in physics. It's what's called the root mean square speed, RMS speed. So if you take that average of the squares and you take the square root of that, you get root mean squared, RMS. You're taking the square root of the mean of the squares. That's how I remember it. And this is a formula for it right here. VRMS, or what we call RMS speed or RMS velocity, is the square root of the average of the squares. Now, what I said on a couple of slides ago is that the average kinetic energy is equal to 1/2 times m times the average of the speed squared. So what I can do is I can replace that with the square of the RMS speed. So this is a key equation that you will want to know and that we're going to actually apply. Is that 1/2 times m times the RMS speed of each molecule is equal to 3/2 times kT. Okay, so let's look at an example problem. And this example problem says, what is the root mean square speed of an oxygen molecule at room temperature? Okay, so let's pull up the equation that we just derived that involves root mean squared speed. There we go. Okay, so I'd write this down first. And then I need to know some information in order to figure out what the RMS speed is. First of all, I'd need to know the mass of an oxygen molecule. And then I'd need to know the room temperature, or what room temperature is. I also need to know the Boltzmann constant, but that's always going to stay the same. So that's 1.38 times 10 to the negative third joules per Kelvin. What is the mass of an oxygen molecule? Well, it's equal to its molecular weight times the mass of a proton. So if you look up the molecular weight of oxygen on your periodic table, you're actually going to see the number 16. But remember, an oxygen molecule is actually O2, so we have 2 oxygen atoms in an oxygen molecule, and that means the molecular weight of oxygen is 32. And then we have to multiply that times the mass of a proton. And if you look at the mass of a proton, you're going to find out it's 1.67 times 10 to the negative 27 kilograms. You multiply those two together and you're going to get the mass of an oxygen molecule. And that's 5.34 times 10 to the negative 26 kilograms. The other thing we need to know for this problem is what is room temperature. Room temperature is approximately 20 degrees Celsius. And 20 degrees Celsius, when you convert that to the Kelvin scale, you just need to add 273 to whatever it is in Celsius. So, is it 273 or 278? Oh my gosh, I can't remember. Actually, I want to say 273, and that means room temperature is about 25 degrees Celsius. Yeah, okay. But I do remember, right off the top of my head, that room temperature is about 300 Kelvin. Some people will quote 298 Kelvin, which tells me that room temperature is about 25 degrees Celsius. Anyway, let's assume that this is room temperature. All right, so now I know everything that I need to know to plug into this equation up here. When we go ahead and plug that all in, we get this expression or this equation. And now I just need to solve that for the RMS speed. And when I do a little bit of math, I find out that the RMS speed squared is 2.32 times 10 to the 5th. Take the square root of that. And it turns out the RMS speed of an oxygen molecule at room temperature is about 482 meters per second. Wow, that's amazing. So you're getting bombarded by oxygen molecules that are going 482 meters per second. RMS, root mean squared. Woo! Thankfully they're really, really super light, so they impart a lot of momentum onto you. Alright, so that's how you'd figure out RMS speed. I hope you found this video informative. I think it's really cool to figure out exactly what temperature really measures. And that's why it took a while, but I wanted you to really deeply understand what was going on behind this equation. Because as we get further into our unit, this number is actually, we're going to find out that this coefficient in front of KT actually changes. Just like it changed when we went from 1 dimension to 3 dimensions. So, an interesting thing to look forward to. Alright, like I said, I hope you found the video informative, and I hope it helps you out with the 10.1 practice. Look forward to seeing you soon. Bye.